Hello everyone, we're at the topic of transistor amplifiers and we're going to drive a circuit model for the AC signals applied to transistor amplifier circuits. So we're going to start with MOSFET amplifiers and we're going to study the response of these transistor amplifier circuits to AC signals. We're going to show that the signal IV equations for transistors are different from the nonlinear IV equations that we've seen so far for MOSFETs, and it's the same for the case of BJT amplifiers. Okay, so let's take a look at a very basic amplifier configuration using MOSFET that you can see in this circuit. And I already included the IV equations because the uppercase and lowercase characters for these current and voltages in the amplifier topic have different meanings, so I decided to type them for you. Okay, and so in order to use the transistor as an amplifier, we need to make sure that it operates in the saturation region. And in the saturation region, here is the current equation that has ID equals to 1 over 2 Kn VGS minus VT to the power of 2, and Kn is this parameter mu and Cox W over L for NMOS transistor that I have here. And so for the beginning, at the start, we are going to neglect the channel length modulation effect, meaning that we're going to assume that lambda is equal to 0. So here is the ID equation for the case of saturation when the transistor operates in the saturation region. And from the KVL in the drain to source loop, I have VDS equals to VDD minus RD times ID. So far, these are the equations when I don't have any signal or I don't have any AC signal applied to the gate of my transistor. Everything is DC up to here. Now assume that I add an AC signal to the DC voltage that I had for my gate. Now the instantaneous gate to source voltage, or this VGS, consists of a DC term and an AC term. So because my gate to source voltage has both an AC and DC term, this ID equation, the drain current, is also going to have an AC and DC term. And I'm going to I can write ID in this format. Now I'm replacing my VGS with DC and AC terms, and I have the same equation that I had before. So small ID is 1 over 2 Kn parentheses VGS plus small VGS minus VT to the power of 2. So I'm going to expand this equation, the term inside the parentheses, and see what I get from this expansion. So I would like to keep the DC parts separate, this one and this one together, and this term here, this small VGS, separately, because I would like to have an equation for the total instantaneous ID current as a term of the DC part and AC part separately. This is my goal. So if I expand this term inside the parentheses, I'm going to have 3 terms. This is purely DC. There's no AC term in this, so I can consider it as a DC part of my total current. This is a term that has AC component in it multiplied by a constant value. And the third term is an AC term that is to the power of 2, or it's a nonlinear part for AC, which can be considered as distortion. Now consider the case when the third term, this term, is much smaller than the second term here. If it is the case, then I can neglect the effect of third term in the whole ID equation. Then I'm going to have only 2 terms in my instantaneous ID equation for this ID, I can write it in terms of DC part or uppercase I, uppercase D for subscript, and lowercase I and lowercase d for the AC part of my total instantaneous drain current. And this is going to happen if the gate to source voltage, the AC gate to source voltage, is much smaller than 2 times the overdrive voltage. So far I applied a voltage, gate to source voltage, that has both AC and DC terms to it, and then assuming that the amplitude of the applied AC signal is small, or under small signal approximation, I was able to write instantaneous drain current, or I sub uppercase D, in terms of a DC current and AC current. So I approximated the total ID current with the DC part and AC part. Let's take a look at the meaning of this approximation. So I had this ID equation before, neglecting the third term, and this is the goal, to write it in the DC as a DC plus AC components. And I have, that is gonna tell me that the AC part, or AC part of the drain current, is related to the AC part of the input voltage, or applied AC signal, in a linear fashion. So ID is a coefficient multiplied by VGS, and this coefficient has a meaning, it has a name, it's called transconductance, or GM. So GM is defined as ID over VGS, and it is equal to Kn times V overdrive, which is the same as 2 times ID, the DC drain current, divided by V overdrive. Everything in this GM equation is DC. So I is DC, the drain current, and V overdrive is the DC part of VGS minus threshold voltage, which is also a constant voltage value. So I was able to relate the small signal current to small signal voltage applied to the gate to source used in a linear way. So ID is equal to GM to VGS. So drain current and gate to source voltage have a linear relationship with each other. So far we have this for the drain current and gate to source voltage. Let's take a look at the drain to source voltage for the AC signal and see how it is related to VGS and ID. Using the drain to source KVL, I have VDS equal to VDD minus RD times ID, and this is the total current, instantaneous current, and this is the total instantaneous drain to source voltage. I was able to approximate ID with upper DC part plus AC part under the small signal approximation. Now I'm going to plug in these two in this ID equation, and now I have VDS, instantaneous drain to source voltage, is equal to VDD minus RD times ID, this is the DC part, minus coefficient multiplied by the AC drain current. So, and this tells me that I can write VDS, the total instantaneous VDS, as a summation of DC part plus an AC part, and this is going to be the DC part of drain to source voltage, and this is going to be, this term here is going to be the AC part of the drain to source voltage. So VDS is going to have, the total instantaneous VDS is going to have two terms, the DC part and AC part. The DC part is this equation here, drain and the power supply minus RD, the drain resistance, and multiplied by the DC drain current, and the AC part is related to ID and VGS in this way. With small v subscript small d small s equals to negative ID times RD, and that is equal to negative GM VGS times RD. So the drain to source voltage is related to drain current and gate to source voltage in a linear way, and they all have a linear relationship with each other. Compare it to the uppercase VDS and the DC terms of drain to source voltage and drain current and VGS, and if you remember from previous lectures, they all have a nonlinear relationship with each other. So under small signal approximation, we can show that the signal parameters quantities have a linear relationship with each other. So the gain of the amplifier voltage gain or small signal voltage gain is defined as this small VDS divided by small VGS, and that is equal to negative GM times RD. And all parameters in GM are related to the DC values of my transistor. So the gain of the signal gain of the transistor is going to be dependent on the DC parameters of my transistor as well as the drain resistance. So now I'm going to use the derived equations for the small signals and to develop a model for the small signal circuit or the small signal equivalent model for this transistor. So I have a 3-terminal device for my MOSFET. One of the terminals is gate, the other one is drain, and the third one is my source. So I'm going to place them on my model, and then I'm going to, knowing that from gate to drain, from gate to source, there's no current flowing from gate to source, or IG is equal to 0. So there's going to be open circuit between gate to source, and the voltage between gate to source is small VGS. Also, I already found that ID and VGS is related by a term called GM. So ID is GM times VGS. ID is the current that flows from drain to source. This is my ID. So I'm going to place a voltage dependent current source between the drain to source, and that is how I relate ID to VGS. So the small signal circuit model for the MOSFET transistor consists of a voltage dependent current source between drain to source, and so our model is missing a parameter, and that is to model the effect of drain to source voltage on the drain current. So if you remember at the start of these derivations, we assumed that lambda is equal to 0, or we neglected the effect of channel length modulation. However, in the ID equation for the MOSFET in the saturation region, takes into account the effect of channel length modulation using a term that is multiplied to the ID current. So I had ID equals to 1 over 2 Kn V over drive to the power of 2 multiplied by 1 plus lambda times VDS, and I use this term in the parentheses to model the effect of channel length modulation, and I use it to show that when VDS increases, the ID is going to also increase because of the decrease in the channel length. So if I want to include that effect in my small signal model, I can add a resistor, as you can see here, between the drain to source. These are out resistor between drain to source, and then my ID, this ID is going to have this 2 terms in this equation. So GM VGS, one effect that comes from VGS, and another term that takes into account the effect of drain to source voltage. So if this VDS increases, the ID value is going to also be increased. Value of R out can be calculated as 1 over lambda times ID. You can look at the reference notes for the detailed derivations of this R sub O. So GM, I already had this GM, which is defined as 2 times I calculated as 2 times ID divided by V over drive. And this is the model, small signal model that I'm going to use to analyze my MOSFET amplifier circuits.